Have you ever seen a cloud that doesn't belong to Earth? Out there, between the stars, are vast shapes of gas and dust, some glowing, some dark, all changing. They are not just scenery. They are the birthplaces of stars, the remains of old ones, the slow bridges between what ends and what begins. From a distance, they look soft, almost calm, but every shimmer marks gravity at work and radiation in motion. A nebula is both a cradle and a grave, holding the chemistry of everything that will ever shine again. As we look closer, the shapes start to tell their stories, some sculpted by shock waves, others by light itself. If you enjoy drifting through these quiet frontiers, a quick like and subscribe helps more explorers find their way here. Let's begin with the clouds of creation. Space between the stars is not empty. It holds a thin mix of gas and dust that stretches across the Milky Way, a quiet background that sets the stage for new stars and records the remains of old ones. Astronomers call these regions nebulae, from the Latin word for cloud. They are not like the clouds over Earth. They are far larger, far thinner, and shaped by light and gravity over long spans of time. From a distance, a nebula can look like a smudge. Up close, with sensitive cameras, it resolves into wide sheets, arcs, and knots that span light years. A light year is the distance light travels in 1 year, about 6 trillion miles, 9.5 trillion kilometers. Some nebulae glow, some simply reflect nearby light, others block light and appear dark. Together, they form a slow, changing framework for how our galaxy builds and rebuilds itself. A nebula often begins as a cold region where atoms drift with little motion. Most of those atoms are hydrogen, the simplest element. Helium is next. There are also traces of heavier elements, such as carbon, oxygen, nitrogen, silicon, and iron. Over time, gravity collects this material into loose threads. Threads meet, form clumps, and become denser. Inside the denser parts, gas pressure and temperature rise. When a clump grows massive and compact enough, the center heats until nuclear fusion can start. Fusion is the process where small atomic nuclei join to form larger ones, releasing energy. When fusion begins, a star is born. Nebulae are not only cradles, though, they are also the gentle remains of stars that have ended their steady phase, and the debris fields of stars that ended more violently. In this way, these clouds record both creation and decay. One useful way to understand nebulae is to group them by how they interact with light. Emission nebulae are the bright showpieces. They glow because high-energy radiation from young, hot stars excites the gas. The most common source is ultraviolet light from massive O-type and B-type stars. Ultraviolet light has enough energy to knock electrons off hydrogen atoms. This makes a region of ionized hydrogen, sometimes labeled H2, pronounced H2. Free electrons later recombine with the protons. As electrons drop back to lower energy levels, they give off light at specific wavelengths. One of the strongest is hydrogen alpha at about 656 nanometers, which appears as a deep red in many images. The Orion Nebula is a classic example, a large cloud where newborn stars and their radiation carve hollows and light the gas from within. Reflection nebulae do not make their own light. They shine by scattering the light from nearby stars. Tiny dust grains inside the cloud scatter shorter wavelengths, bluer light, more effectively than longer wavelengths, redder light. This is similar to why Earth's daytime sky looks blue. The result is a soft, pale blue glow, often seen around young star clusters. The dust grains vary in size and composition, so the exact shade and texture can change from place to place. The Pleiades star cluster is a familiar case. Bright blue starlight sweeps across faint dust, giving a calm, powdery halo to the scene. Dark nebulae are the opposite in appearance. They are dense enough in dust to block the light behind them. Against a bright background, they appear as shadows with clear edges and shapes. The famous Horsehead Nebula shows this effect. A thick column of dust stands out in silhouette against a red field of glowing hydrogen. Inside such dark clouds, starlight is weak. That allows gas to cool and settle. In the coldest, densest pockets, often called molecular clouds because hydrogen pairs up into H2 gravity, has the best chance to pull matter together. These are the nurseries where stars begin in secret, far from direct light. Not all nebulae point to birth. Some record the aging of stars, like the Sunday after. A sun-like star uses most of its core hydrogen. It expands into a red giant. In that phase, it sheds its outer layers. The hot core left behind, called a white dwarf, lights the thin gas around it. This creates what astronomers call a planetary nebula. The name is historical. Early telescopes showed round, planet-like disks, though these objects have nothing to do with planets. A planetary nebula is a glowing shell set adrift, slowly fading over tens of thousands of years as the gas spreads out and the central white dwarf cools. There is also a more violent end. When a very massive star runs out of fuel to support its weight, it collapses and explodes as a supernova. The blast tears the star apart and throws its outer layers into space at thousands of miles per second. The expanding debris forms a supernova remnant, a web of filaments, arcs, and knots that can span dozens of light years. The Crab Nebula is one of the best known. It is the remnant of a supernova recorded by observers in the year 1054. Supernova remnants are important because they spread heavy elements such as iron, calcium, and nickel through space. They also drive shock waves into the surrounding gas, compressing it and shaping where future stars may form. Nebulae look thick in photographs, yet they are extremely thin by everyday standards. In many regions, a cubic centimeter, the volume of a sugar cube, may contain only a few hundred atoms. Air at sea level contains roughly 10 to the power of 19 molecules per cubic centimeter, an amount so much higher that it makes the nebula gas seem like nothing in comparison. However, spread this almost nothing across tens or hundreds of light years, and it becomes a structure large enough to glow, scatter light, and cast shadows. Dust makes up only a tiny fraction of the mass, but it plays an outsized role. Dust grains, made of silicates and carbon compounds, absorb and scatter starlight. By blocking light, they help gas cool. Cooler gas loses pressure support and can collapse more easily under gravity, setting the stage for star formation. Dust also provides surfaces where simple molecules can form and survive, which is important for the chemistry of future planetary systems. The same nebula can look very different when viewed at different wavelengths. Visible light often shows bright hydrogen emission and the shapes carved by hot stars. Infrared light can pass through dust more easily, revealing stars that are still forming within cocoons. Radio observations can trace cold molecular gas, mapping where dense regions collect before new stars turn on. Each band of the spectrum adds a layer of information. By comparing them, astronomers build a more complete picture of a cloud's temperature, density, and motion. Spectroscopy is the main tool for turning color into data. A spectrograph spreads light into its component wavelengths and produces a pattern of lines. Bright lines mark wavelengths where atoms or ions emit strongly. Dark lines mark where light is absorbed. Hydrogen's bright red hydrogen alpha line is common in emission nebulae. Doubly ionized oxygen, written as O3, produces green-blue lines near 500.7 nanometers. Singly ionized sulfur, S2, produces lines near 671.6 and 673.1 nanometers. Some of these lines are called forbidden in old terminology. That word means the transitions are unlikely at the densities found in Earth-like conditions, where atoms collide often and lose their chance to emit. In the thin gas of a nebula, an atom can stay in a delicate, excited state long enough to release its light. These rare lines are useful because they carry information about temperature, density, and the level of ionization. Scattering also carries clues. In reflection nebulae, small grains scatter blue light more than red. This size-dependent behavior is one reason blue tones appear. Larger grains contribute a different style of scattering that spreads light more uniformly and softens sharp edges. By modeling how light is scattered and absorbed, astronomers estimate how much dust is present and how it is distributed. This matters because dust shapes what we can see, but it also helps set the pace of star formation by controlling how quickly gas can cool. Inside star-forming regions, young stars push back on their surroundings. They produce strong stellar winds, fast flows of charged particles and jets that shoot along their rotation axes. These winds, jets, and intense radiation carve bubbles and pillars in the nearby gas. The popular pillar shapes seen in some images are columns of denser material left behind, while the lower density gas around them is cleared out. At the edges of these structures, shock fronts form where fast-moving material hits slower gas. Shocks compress and heat the gas, which then gives off light in specific lines that trace the shock conditions. By mapping those lines, astronomers can follow how energy from young stars changes the cloud and sets boundaries for where the next generation of stars may form. Even in dark clouds, motion never stops. Gravity draws material toward dense cores. Turbulence random, swirling motion on many scales stirs the gas and can both help and hinder collapse. Magnetic fields thread through the gas and dust, adding an extra form of support. Observations of polarized light, which indicates alignment of dust grains in magnetic fields, help trace this invisible structure. The balance among gravity, gas pressure, turbulence, and magnetic fields decides which parts of a cloud will form stars, how many will form, and how massive they will be. This is why some regions become rich clusters, while others make only a few stars. When a dense core collapses, it does not fall straight inward. Conservation of angular momentum, an object's tendency to keep its spin, causes the collapsing material to form a rotating disk around the young star. This is a protoplanetary disk. Dust grains in the disk stick together, forming pebbles, then larger bodies. Over time, these can grow into planets. Radiation from the central star and winds from nearby massive stars can blow away gas from the disk's surface. In strong radiation fields, the outer parts of disks evaporate, changing where and how planets can form. Infrared and radio observations can image these disks, showing gaps, rings, and spirals. Such features often signal places where young planets may be shaping the gas and dust. Planetary nebulae provide a different kind of detail. As a sun-like star sheds its outer layers, the outflow may vary with time and direction. Magnetic fields, rotation, and close companion stars can all shape the gas. This creates shells, rings, and bipolar lobes, two opposing bubbles with narrow waists. The central white dwarf can be extremely hot, lighting the gas with a clean, bright spectrum. Over thousands of years, the shell expands and thins. The faint outer edges record earlier, slower winds. The bright inner regions mark later, faster ones. By measuring expansion speeds and sizes, astronomers estimate ages and learn how mass loss proceeds near the end of a star's life. Supernova remnants add strong shocks and high-energy particles to the picture. In young remnants, the shock front moves supersonically into surrounding gas, heating it to millions of degrees. That hot gas emits X-rays. As the shock slows, it compresses gas and dust into filaments that shine in optical lines. Magnetic fields get amplified in the shock, and electrons spiral in those fields, giving off radio waves through a process called synchrotron radiation. Together, these emissions let scientists track the energy budget of the explosion and how it changes the local environment. Supernovae also form some elements directly and create conditions where dust can form or grow. Later, parts of that dust will be mixed into new clouds and new systems. The chemistry inside nebulae is simple in parts and complex in details. Hydrogen dominates, but the small fractions of other elements matter. Carbon and oxygen help set cooling rates through their emission lines. Nitrogen and sulfur add additional paths for energy to leave the gas. Molecules such as carbon monoxide, CO, and water, H2O, trace dense cold regions. In very cold, well-shielded cores, even more complex molecules can exist. These are not life, but they are steps along the road to the chemistry we find on planets. Dust grains serve as meeting places where atoms can join and where fragile molecules can survive. Although images of nebulae look dramatic, the timescales are long. What looks like a sharp arc is often the edge of a slow wave moving over tens of thousands of years. A bright knot may trace where a jet met a denser patch and glowed for a while before fading. Over millions of years, star-forming regions open and disperse as young stars heat and stir the gas. The material they drive away does not vanish. It becomes part of the larger interstellar medium again, to be drawn into some future cloud. The galaxy recycles its material this way, and the balance between star formation and feedback from stars helps set the overall pace. Astronomers turn images into measurements with a small toolkit. Spectral lines reveal temperature, density, and motion via the Doppler shift, showing which gas is calm and which is falling inward. Infrared maps locate warm and cool dust. Radio maps trace molecules that mark the coldest, densest pockets. Layered together, these data outline how a region builds stars rarely in one burst, but in clusters of subgroups with different ages spread across the cloud. Dust sits at the center of both the physics and the measurements. Though faint and thin, it shapes what we see and what can form. Grains typically to 0.1 micrometer, about smoke-sized, are hard silicates, olivine, pyroxene, carbon-rich solids, metallic iron, and, in cold zones, ice coated with water, methane, or ammonia. They scatter and absorb starlight, changing colors and hiding depths, re-emit energy in the infrared, signaling temperature, and provide surfaces where molecules assemble. By setting how light moves and how chemistry proceeds, Dust controls both the look of nebulae and the pace of collapse that leads to planets. These grains form in the atmospheres of aging stars and in the debris of dying ones. Red giants and asymptotic giant branch stars expand, cool, and shed their outer layers. As that gas moves away and cools, atoms stick together and condense into solids. Supernovae contribute too, throwing out gas and dust at thousands of miles per second. Shock waves from the blast can destroy grains near the center, but farther out, many survive. Others regrow later in calmer gas. Over time, this material blends into the interstellar medium, the thin mix of gas and dust that fills the space between stars. Atoms and molecules can freeze onto grain surfaces like frost, adding layers that change how the grains interact with light. Starlight passing through dusty regions does not remain the same. Some light is absorbed and heats the grains. Some is scattered in new directions. Shorter wavelengths, which we see as blue, scatter more easily than longer wavelengths like red. This is similar to the reason Earth's sky is blue. The result is interstellar reddening. Stars seen through dust look dimmer and redder than they truly are. The stars are not changing color. The dust is filtering their light. Wide swaths of the Milky Way show dark lanes and rifts, where dust blocks the bright star field behind it. Through small telescopes, these lanes show a textured look, like smoke with structure rather than a simple hole in the sky. The Horsehead Nebula in Orion is a clear example. It is a dense column of gas and dust silhouetted against a glowing background of hydrogen emission. Nearby, hot stars bathe the region in ultraviolet light. That light erodes the edges of the column grain by grain, a slow process that sculpts the outline over time. The feature is not solid. It is a thick region amid thinner gas. Farther away, in Ophiuchus, the Snake Nebula shows a long dark filament against a rich star field. Turbulence, gravity, and magnetic fields have drawn the gas and dust into a thread. Within such filaments, small dense pockets often collect. Given time and the right conditions, some of those pockets will collapse and form stars. Dust both hides and reveals. Around bright stars, small angle scattering makes faint blue halos in reflection nebulae. At the same time, absorption makes strong shadows and outlines. Energy absorbed by grains does not vanish. The grains warm slightly and re-emit that energy at infrared wavelengths. To our eyes, a region may look dark. In infrared images, it glows softly. This shift is useful because infrared light passes through dust better than visible light. Observations at infrared wavelengths can show stars still wrapped in their birth cocoons and disks forming around them. Many grains tend to align with the galaxy's magnetic field. The alignment is weak but measurable. When starlight passes through a cloud where grains are aligned, the transmitted light becomes slightly polarized, meaning its waves vibrate more in one direction than others. Instruments that measure polarization can map the direction of magnetic fields across dusty regions. This matters because magnetic fields help support clouds against collapse, channel flows of gas, and interact with turbulence. Dust, despite being a small fraction of mass, carries an imprint of these larger invisible forces. Dust is central to how planets form. In cold, dense clouds, grains collide and stick, helped by frost coatings that act like glue. Small grains become pebbles. Pebbles gather into clumps and larger bodies. Inside disks around young stars, this growth continues until rocky planets, icy bodies, and the cores of gas giants can form. Every solid surface we know, asteroids, moons, planets, and rings, can trace its origin to grains in a nebula. Dust also influences the temperature of gas. By absorbing and re-emitting radiation, it helps gas cool. Cooler gas loses pressure and is more likely to collapse under gravity, which speeds up star formation in the right places and slows it where radiation is strong. The colors seen in nebulae arise from both gas emission and dust effects. In emission regions, ultraviolet light from hot young stars ionizes hydrogen and other elements. When electrons recombine with ions and drop to lower energy levels, they emit light at specific wavelengths. Hydrogen alpha, at 656 nanometers, is a strong red line. Doubly ionized oxygen, O3, near 500.7 nanometers, gives a green-blue light. Singly ionized sulfur, S, near 671.6 and 673.1 nanometers, gives a deep red-orange. These emissions can be weak in dense laboratory conditions because atoms collide too often and lose their chance to radiate. In the thin gas of space, the emissions are clear. In reflection regions, dust scatter favors blue light and makes pale blue glows around star clusters. In dark regions, light is absorbed and the dust appears as silhouettes. Across all cases, the same physics absorption, emission, and scattering controls the view. Even a trace of dust changes observations. A cloud with only a few hundred atoms per cubic centimeter, which is emptier than the best laboratory vacuum, can dim starlight noticeably over long distances. Astronomers must correct for extinction the combined dimming from absorption and scattering when measuring distances and the brightness of objects. If they do not, distant stars and galaxies appear fainter and redder than they should, leading to errors. Maps of dust based on starlight colors, infrared emission, and radio data help apply these corrections. The veil is thin, but over hundreds or thousands of light years, it has a measurable effect. Dust grains do not last forever. Harsh ultraviolet radiation can break apart their outer layers. Shock waves from supernovae and strong stellar winds can shatter grains into smaller pieces, yet the cycle continues. Fragments and molecules in calmer regions gather again onto surviving grains, or new grains condense in stellar outflows. The interstellar medium is a place of slow recycling. Material moves from stars to space and back again, with dust as the carrier of metals and complex molecules between generations. A dark nebula is not an empty hole, it is structure. The visual impression of an absence comes from strong contrast against a bright background. Within those shapes, the gas and dust are thick enough to block visible light, yet still thin compared with any air we breathe. The structure hints at the forces at work: gravity pulling inward, turbulence stirring the gas, and magnetic fields guiding it. Slight differences in density grow with time. Where density becomes high enough and cooling efficient, collapse can begin and a star can form. Among the best places to see these ideas in action is the Orion complex, a broad region of gas, dust, and young stars a little over 1,300 light-years away. It is not one object, but a linked group: dark clouds, bright emission regions, and large arcs shaped by stellar winds and past explosions. A giant arc, called Barnard's Loop, sweeps across much of the constellation. If our eyes were sensitive to its faint red emission, it would appear as a wide bow curving around Orion's bright stars, spanning a large part of the sky. The arc likely marks the edge of a large cavity blown by winds and supernovae from earlier generations of massive stars. Inside that cavity, fresh star formation is active. Toward the center lies the Orion Nebula, where a massive molecular cloud is collapsing in patches. A compact cluster of hot young stars called the trapezium sits near the core. Their ultraviolet light ionizes the surrounding gas, and their winds push it aside, creating a hollowed-out, glowing cavity. Pillars and ridges mark where denser clumps resist the flow. The process is energetic. Gas evaporates from the surfaces of dense fingers. Shock fronts brighten, where faster winds strike slower gas. What looks like a smooth glow from far away resolves into fine texture, arcs, knots, and cavities carved by radiation and motion. Near the trapezium, many young stars show small, dark, disk-like shapes when viewed against the bright nebula. These are protoplanetary disks, often nicknamed proplids. They are dusty, rotating structures around young stars where planets can form. Some show bright edges facing the cluster, where strong ultraviolet light heats and drives gas off the disk surface. Others are more sheltered and appear as calm ovals. Observations at infrared and radio wavelengths reveal gaps and rings in some disks, features that may be linked to forming planets. The Orion Nebula is close enough that it can be studied across the spectrum with high detail. In visible light, hydrogen's red emission dominates, with green-blue light from oxygen adding contrast and faint blue reflection from dust on the outskirts. Infrared views show stars still wrapped in dust and reveal the warm glow of grains themselves. X-ray observations highlight hot gas from sharks and young stars with strong magnetic activity. Radio maps trace cold molecular gas around and behind the glowing region. Together, these datasets form a layered view where gas is hot or cold, dense or thin, moving toward or away from us. The larger Orion complex includes the Horsehead Nebula and the Flame Nebula, both tied to the same broad molecular cloud system. Energy from one area can trigger changes in another. When young, massive stars heat and push on nearby gas, they can compress other parts of the cloud. Compressed gas can cool and collapse, starting a new round of star formation. In this way, activity propagates through the region over time. The mix of red emission from hydrogen, blue scattering from dust, and dark lanes of absorption reflects the balance of radiation, density, and composition in each part. Barnard's loop frames the activity on a bigger scale. It outlines where winds and past explosions have swept gas into a shell. Inside that shell, gravity, magnetic fields, and turbulence divide the remaining gas into filaments and clumps. Along some filaments, star clusters form in strings. The pattern is not random. It follows the combined effects of pressure waves, cooling, and self-gravity. In Orion, these patterns are close enough to map in detail, which is why the region serves as a natural laboratory for testing ideas about how stars and planets form. Even without instruments, the Orion Nebula is one of the few star-forming regions visible to the unaided eye from dark sites. It appears as a small blur in Orion's sword. Binoculars show a soft fan shape. Small telescopes reveal curved layers of light with a bright core. The difference between what we see and what instruments record is a matter of sensitivity and wavelength, not a different object. The same structures picked out by hydrogen, oxygen, and dust are there, just beyond our eyes' limits. Dust leaves clear fingerprints in light. Silicate grains create features near 10 and 18 micrometers. broad bumps in the blue and ultraviolet point to carbon-rich materials. In the coldest zones, ice coatings add their own infrared bands. By measuring these signatures, astronomers infer grain sizes, compositions, and temperatures, and map where conditions favor surface chemistry, places where complex molecules can form on grains and later return to space when warmed. Those same processes shape nearby systems in real time. As young stars in Orion brighten, their radiation erodes surrounding clouds. Disks near strong UV fields lose gas quickly and trend toward rocky outcomes. Disks protected in deeper pockets retain gas longer and can build giants. Gas pushed from the center is not lost. It mixes into the wider interstellar medium and may later collect along cavity edges to seed new clouds. The roles remain steady even as scenes change slowly. Light heats and drives flows. Dust cools and shades. Gravity gathers, and material cycles through phases that set the next steps. A clear comparison sits near Alnitak, the eastern star of Orion's belt. The Horsehead Nebula is a dense, dark column silhouetted against a glowing background dust-blocking starlight. The Flame Nebula is a bright field where ionized gas shines on its own. Side by side, they show two outcomes of the same ingredients: how radiation, dust, gas pressure, and gravity, acting together over time, can either carve a silhouette or light a cloud from within. The Horsehead, also called Barnard 33, is not a solid object. It is a dense column of cold gas and dust that stands in front of a red emission field named IC 434. That background is hydrogen gas lit by strong ultraviolet light from hot stars nearby, including Sigma Orionis. Ultraviolet, often shortened to UV, is light with shorter wavelengths than purple that human eyes cannot see. UV light strips electrons from atoms, leaving ionized gas that later glows as electrons return. Against that glow, the Horsehead appears as a sharp, dark outline. The familiar head and neck shape is an accident of perspective, but the structure behind it is real: a thick cloud core inside a larger sheet of gas. The darkness is not empty space. Dust grains inside the column absorb and scatter visible light, making the cloud look opaque. A dust grain is a tiny solid particle made of silicates, carbon, and sometimes ice. Most are smaller than a micron. The gas in the Horsehead is only a few dozen degrees above absolute zero, which is 459.67 degrees Fahrenheit, 273.15 degrees Celsius. Cold gas has low pressure, so gravity can gather it into clumps. Deep inside, where the dust blocks UV light, molecules such as hydrogen, H2, can survive. Over long periods, some clumps may collapse and form stars. At the edges, the story is different. UV light heats and erodes the surface, a process called photoevaporation. The thin, bright rim along the crest marks where the outer layers are being stripped, atom by atom. On the sky, the Horsehead looks small, but it spans several light years. A light year is about 6 trillion miles, 9.5 trillion kilometers. The column could fit many solar systems across its width, yet it is fragile on cosmic scales. Radiation is eating away at it, and in a few million years the outline we know will fade as the material blends back into the wider Orion complex. For now, the sharp silhouette is useful. It turns invisible dust into a visible shape, allowing astronomers to study how light shapes a surface and how dense cores resist that erosion. Not far away is the Flame Nebula, NGC 2024, close to the glare of Alnitak. At first glance, it seems like the opposite of the Horsehead. Instead of a black cutout in front of a red sheet, the flame is a bright cloud crossed by dark lanes. The same UV radiation that carves the Horsehead also powers the flame. UV from Alnitak ionizes hydrogen and other gases, so the cloud glows. Hydrogen's red emission dominates, while oxygen and nitrogen add green and blue tones in long exposure images. The flame look comes from bright ridges broken by cooler, dusty filaments that block light along our line of sight. Those dark bands are not gaps in the cloud. They are lanes of dust and cold gas that sit in front of the glowing regions. Magnetic fields and pressure differences help draw material into filaments. A magnetic field is a force field created by moving electric charges. In space, it can guide how charged gas flows. The filaments act like baffles, shaping how radiation and winds move through the cloud. In visible light, the dust hides the youngest stars. In infrared light, longer wavelengths our eyes cannot see, those hidden stars show up as warm points. Surveys in the infrared reveal clusters of newborn stars still wrapped in their birth cocoons. The flame also shows clear ionization fronts. An ionization front is the boundary where UV-lit gas meets colder, neutral gas. Along that edge, electrons and ions recombine and emit light, and the gas is pushed and heated. The fronts look like veins of brightness that trace the contact between hot and cold zones. Pressure differences across the front create waves and ripples. Over time, these ripples can compress nearby gas and seed new places where gravity can take hold. The physics is steady. Radiation strips electrons, electrons recombine, light is emitted, and gas flows away from high-pressure regions. Seeing the Horsehead and the flame together helps separate effects. The Horsehead shows how dust blocks light and shields a core. The flame shows how gas lights up under UV and how dust carves shadows within a bright field. Both scenes are the result of the same causes acting on different arrangements of material. Both lie within a network of clouds tied to Orion's belt and sword, where winds from hot stars, past shocks, and gravity have built arcs, pillars, and knots. When early long-exposure photographs captured the Horsehead at the end of the 1800s, the dark profile stood out clearly against IC 434. The outline matched a familiar shape, which made it easy to remember, but the useful part is the physics behind the edge, the sharp border marks where radiation meets dense gas. Modern digital images add more context: fine filaments around the main, faint stars peeking through thinner parts, and the thin, luminous skin where the surface is heated. In the flame, higher resolution turns the bright field into a lacework of ridges and threads, each tracing a change in density or field direction. For visual observers, Alnitak's glare makes the flame a challenge. Under dark skies, the flame can be seen as a faint glow next to the star, with dark cuts that look like branches. A Horsehead is harder. It usually needs a special hydrogen beta filter that passes the red light from hydrogen while reducing the star field, plus very steady air and a large telescope. Even then, it appears as a small notch on the edge of the IC 434 glow. Knowing the layout helps. Alnitak, then the flame, then a faint strip of red, and along it the small shape of the Horsehead. South of Orion, another set of tall structures shows what UV light does to dense clouds on a larger scale. In the Eagle Nebula, catalogued as M16, long columns of gas and dust stand inside a bright emission region. These are the pillars of creation. Each column is several light years tall. They look solid in pictures, but they are low-density gas supported by internal pressure and shaped by radiation. Near the tops of the columns, UV light from nearby hot stars heats and peels away the surface layers. This photoevaporation creates a thin, bright skin and sharp edges. Inside the columns, the gas is cooler and denser. Cooler gas radiates energy away more efficiently, which lowers pressure and lets gravity work. Small, dense pockets, astronomers call them globules, can form inside. Some of these pockets collapse into protostars, which are young stars not yet hot enough for fusion in their cores. At the pillar tips, shock fronts ripple, where fast hot gas hits the cooler column. A shock front is a moving boundary where pressure, density, and temperature jump. Shocks can squeeze gas and help trigger collapse in the pockets below them. The famous Hubble image from 1995 showed 3 main columns lit by nearby stars, with bright elephant trunk tips and a field of emission behind them. That view made the structure easy to recognize. Later images with finer cameras added detail along the edges and revealed more small knots. The James Webb Space Telescope's infrared images went deeper into the dust. Infrared passes through dust more easily than visible light, so Webb showed stars forming inside the columns and traced warm dust along the surfaces. Instead of hiding, the inner parts glow softly at longer wavelengths, which makes it possible to measure temperatures and densities across the scene. The Eagle Nebula is about 7,000 light-years away in the direction of the constellation Serpens. The young cluster NGC 6611 sits nearby and provides the radiation that shapes the pillars. The cluster is only a few million years old, which is young in stellar terms. Stellar winds, fast flows of charged particles, push outward from the hot stars. These winds and the UV light together clear cavities, leaving bright walls where the gas is dense enough to shine and dark notches where dust still blocks the view. As the cavity expands, fresh parts of the original cloud are exposed and eroded. The shapes we see, pillars, arcs, and caps, mark different stages in that process. Gas in the bright parts of M16 emits strongly at specific wavelengths. Hydrogen alpha at 656 nanometers gives much of the red. Doubly ionized oxygen at 500.7 nanometers adds green-blue tones. Filters that isolate these lines allow instruments to map temperature and ionization across the region. In the infrared, bands from warm dust and ices appear, and small grains glow after absorbing UV photons and re-emitting the energy. Polarization measurements show how dust grains align and trace the magnetic field. This mix of tools builds a layered picture of how energy moves from the cluster into the cloud. Timescales in the Eagle Nebula are long compared with a human life. A column can persist for hundreds of thousands of years, but the outer skin changes as fronts move and as small clumps detach and drift. A young star inside a column can switch on, drive a jet, and blow a small cavity into the surrounding gas. A jet is a narrow, fast outflow along a young star's spin axis. It can shock the gas it hits and leave thin tracks that fade as the gas cools. These local changes add fine structure, while the global trend erosion from the outside collapse in protected pockets continues. The columns are only one part of a larger cloud. Around them are arches and knots formed by the same feedback. Some areas show hollow shells where earlier stars have already cleared out gas, leaving clusters in the open. Other areas still hold cold, dense molecular gas. A molecular cloud is a cold region where hydrogen is mostly in H2 form and where molecules such as carbon monoxide, help trace the gas. Radio maps of CO outline the mass of the cloud beyond the glowing edges. Combined with optical and infrared data, those maps show where material remains to fuel future star formation. Distances and brightness in regions like Orion and the Eagle are affected by dust. Extinction, the dimming of light by dust, makes objects look fainter and redder than they truly are. To correct for extinction, astronomers compare colors to standard values and use infrared and radio maps to estimate dust content along the line of sight. Without that correction, stars can appear older or less massive than they are. In the Orion Belt area, the bright stars and the dusty lanes around Alnitak make these corrections important when measuring star counts and ages in the flame. Magnetic fields matter in both places. In the flame, polarized starlight shows field lines that run across some of the dark lanes, suggesting that the field helps organize the filaments. In the Eagle, polarization maps show fields draped around the pillars and sometimes running along them, which can slow collapse across the field while allowing flows along it. The balance among gravity, gas pressure, turbulence, radiation, and magnetic fields decides where stars form and how many form at once. Spectra carry composition clues. Silicate dust leaves broad absorption features near 10 micrometers and 18 micrometers. Carbon-rich materials leave bumps in the blue and ultraviolet. In very cold parts, ice features appear in the infrared, pointing to water, carbon dioxide, and other simple ices on grain surfaces. These features change with location. Near strong UV sources, ice mantles thin and grains shrink, while deeper inside clouds the mantles grow. The grain size and mix determine how strongly light is scattered or absorbed at each wavelength. Observing the area around Alnitak shows how a bright O-type star affects its surroundings. O-type stars are massive, hot, and short-lived. They produce intense UV light and strong winds. The flame sits in that radiation field and glows. The horsehead sits in the same field but appears dark because it is in front of the glowing sheet and is dense enough to block it. In the Eagle, a small cluster of massive stars provides a similar environment, but the geometry and cloud mass produce tall columns instead of a single sharp silhouette. The differences in shape tell us about starting conditions: sheet versus clump, uniform versus filamentary, and near versus far from the UV source. Jets from young stars add a sharper, directional imprint to these regions. In Orion and in M16, narrow, collimated streams punch into surrounding gas and light up compact shock knots called Herbig-Haro objects. These knots radiate in hydrogen, sulfur, and oxygen lines. Taken years apart, images show them shifting across the sky. Those proper motions, combined with Doppler speeds, give true space velocities and reveal how each jet is tilted and how the local gas is flowing. While jets trace outflows, radiation quietly edits the disks themselves. Close to the brightest sources, UV light strips gas and sculpts sharp, sunlit rims, conditions that tend to favor rocky outcomes over gas giants. In more sheltered pockets, disks retain gas longer and can grow massive planets. Infrared and radio maps resolve rings and gaps that likely mark young planets reshaping their birth material. In Orion's core, many disks show bright, heated faces toward the trapezium cluster, direct evidence of photoevaporation. In M16, compact sources at pillar tips reveal very young stars beginning to alter their immediate surroundings. Threading through all these scenes is a short list of drivers acting on gas with different densities and shapes. UV light ionizes and heats surfaces. Dust absorbs, scatters, and re-emits that energy. Gas pressure rises and falls as it heats and cools. Gravity gathers mass where shielding lets gas cool enough to collapse. Magnetic fields guide flows and slow collapse across field lines. Winds and shocks compress and stir the medium. What we record depends on wavelength, resolution, and viewing angle, which is why visible, infrared, radio, and X-ray images each supply a different layer of the same map. South along the Milky Way, beyond Orion's crowded lanes, the Carina Nebula, NGC 3372, shows these processes at a larger, louder scale. It is a sprawling complex lit by many hot, young stars, with volumes that would swallow the familiar Orion Nebula many times over. The layout is busy yet patterned. Bright walls where gas is heated and ionized, dark lanes where cooler, thicker material blocks visible light, and between them, pillars, knots, and hollowed cavities. Here, radiation, winds, gravity, magnetic fields, and time work together to carve structure and set the next round of star formation. At Carina's center lie several clusters of massive O-type stars. O-type stars are very hot and very bright. They shine mostly in ultraviolet UV light that our eyes cannot see. UV light strips electrons from atoms, turning neutral gas into ionized gas that glows when electrons recombine. The same stars also drive fast stellar winds, streams of charged particles moving thousands of miles per second that push the gas outward. Where winds and radiation meet denser clumps, they carve arcs and bowls and leave behind tall columns whose cores are thick enough to resist for a while. The shapes we see are the record of that ongoing push and pull. One star in Carina draws special attention, Eta Carinae. It is a massive, unstable system that changed the way astronomers think about stellar outbursts. In the 1,840 seconds it went through the Great Eruption, brightening until it became the second brightest star in the night sky. It did not explode as a supernova then. Instead, it ejected several suns' worth of material at high speed. That material formed the Homunculus Nebula, a small hourglass-shaped cloud inside the larger Carina complex. The lobes shine in reflected light and in infrared because warm dust re-emits the absorbed energy. Shocks from the outflow plowed into nearby gas, adding turbulence and compressing patches that later made new stars. Eta Carinae remains variable and is expected to end as a true supernova in the future, but the exact timing is unknown. Carina's overall appearance comes from energy moving through gas. Radiation heats exposed surfaces and drives photoevaporation, the slow loss of gas from a sunlit face. Winds sweep out bubbles. Where a fast flow hits slower gas, a shock front forms. At a shock, pressure, temperature, and density jump. The hot, shocked gas can reach millions of degrees and produce X-rays. Cooler, post-shock gas emits invisible lines such as hydrogen alpha, deep red, and doubly ionized oxygen near 500.7 nanometers, green-blue. Long, bright rims trace these boundaries. Behind them, cooler gas and dust remain in shadow. In those protected zones, molecules survive, and gravity can act more easily. Magnetic fields thread through Carina. Dust grains tend to align with field lines, so starlight passing through dusty regions becomes slightly polarized. By measuring that polarization, astronomers map the direction of the field. The field does not stop gravity, but it can slow collapse across the field, and guide flows along it. In images of Carina, many filaments trace curved paths that match patterns seen in polarization maps, a sign that magnetism organizes part of the structure. Turbulence, random motions on many scales adds texture. Together, gravity, pressure, radiation, magnetic fields, and turbulence make the braided look. Long strands, bent layers, and cavities that join and separate. The energy budget is large. The combined brightness of Carina's central clusters produces enough UV to ionize gas across hundreds of light years. Stellar winds add mechanical pressure that sweeps up shells. At the edges of those shells, compressed gas can cool, increasing its density until parts of it begin to collapse. New clusters then form along the rims. This collect and collapse cycle repeats at different scales. In optical images, Carina shows sharp red walls and pale interiors. In infrared, warm dust adds a soft glow. In X-rays, hot inner gas fills some cavities. Each wavelength isolates a different part of the process and shows that the region is not static. Colors in Carina are tied to physics, not paint. Hydrogen alpha marks ionized hydrogen. Oxygen and sulfur lines add other hues. Dust absorbs and scatters visible light and re-emits at infrared wavelengths. The darkest patches in visible images often shine gently in infrared, revealing warm grains and hidden stars. Many of the youngest stars are invisible in ordinary photographs, but appear as points in infrared maps. Around some of them, protoplanetary disks flat. Rotating disks of gas and dust show rings and gaps in radio and infrared observations. Those patterns hint at zones where young planets may be gathering material and shaping the disk. Carina also contains bipolar flows and jets from newborn stars. A jet is a narrow outflow that leaves a young star along its spin axis. Where the jet plows into surrounding gas, bright knots called Herbig-Haro objects appear. They emit in lines of hydrogen, oxygen, and sulfur and drift over time. By tracking their motion across the sky in images taken years apart, astronomers measure their speeds and directions. In Carina, many such jets thread the brighter walls and pillars, adding small-scale structure to the larger scene. The scale can be hard to picture. A single bright ridge may run for dozens of light years. A light year is about 6 trillion miles, 9.5 trillion kilometers. A pillar that looks like a finger in a photo can be several light years tall, yet it is made of gas so thin that a cubic centimeter may contain only a few hundred particles emptier than any vacuum chamber on Earth. Still, when spread across great distances, that gas is enough to glow, to block light, and to build new stars when it cools and gathers. Invisible light, glare from bright clusters, can hide detail. Filters that pass only certain wavelengths, such as hydrogen alpha or the lines of oxygen and sulfur, remove much of the starlight and isolate the glowing gas. Narrowband images made this way reveal ripples on the surfaces of walls and the thin skins on pillar edges. Infrared views add the locations of embedded sources and warm dust. Radio maps trace molecules like carbon monoxide, CO, which mark cold, dense gas that does not shine in visible light. Combined, these views act like layers in a diagram, each one filling in a different piece of the structure. Carina helps explain how massive stars shape their neighborhoods. O-type stars live fast and die young. Before they end, their radiation and winds create bubbles and shells and compress nearby gas. After they end, supernova shocks run through the same region and stir it again. Heavy elements made in massive stars. oxygen, silicon, iron, and more, spread into the wider interstellar medium. Later, that enriched gas becomes part of new clouds and new disks. In Carina, all of these steps are visible at once in different places, so the region serves as a natural case study for feedback between stars and their birth clouds. The Sun likely formed in a region that once looked like a smaller version of Carina, near other young stars, with UV light shaping the outer layers of its natal cloud. In strong radiation fields, outer disk gas can evaporate faster, favoring rocky planets over gas giants. In more sheltered parts, disks keep gas longer. Observations in Carina of disks near hot clusters and farther away show that environment matters for how planetary systems grow. Toward the bulge of the Milky Way, another pair of clouds shows the range of nebula behavior in a smaller field. The Lagoon Nebula, M8, and the Trifid Nebula, M20. They lie in the direction of Sagittarius and appear close together in the sky, though in space they are separated by thousands of light years. Both are visible in wide field photographs as a blend of red emission, blue reflection, and dark dust, but each has its own structure and source of light. The Lagoon Nebula spans more than 100 light-years. It is a classic H2 region, an area of ionized hydrogen powered by UV radiation from young, hot stars. Near its center is the cluster NGC 6530. The cluster's brightest members ionize the surrounding gas and drive winds that clear cavities. Along the edges of those cavities, dust lanes cut across the glow and give the nebula its lagoon look. In small telescopes under dark skies, the lagoon shows as a broad, soft fan with darker streaks. Deeper images reveal folds and filaments. A bright, compact zone within, called the hourglass, not the planetary nebula with the same nickname, marks where intense radiation lights a denser region from the inside. The hourglass outlines how a local pocket can shine more strongly, while the nebula around it spreads light more evenly. The lagoon's gas emits at the same key wavelengths common to star-forming regions. Hydrogen alpha provides much of the red. Oxygen and nitrogen add contrast. Dust absorbs and scatters light, and also glows in infrared after absorbing UV photons. Many newborn stars sit inside dusty cocoons and appear mainly in infrared maps. The newborns drive small outflows and sometimes jets that create knots along their paths. Winds from the cluster push outward, compressing nearby gas into rims and globules. In those compressed zones, gravity can take hold and begin the next round of collapse. Just above the lagoon in our view is the Trifid Nebula. The name Trifid refers to the dark dust lanes that divide its bright face into 3 or 4, depending on the view, lobes. The Trifid is a compact example of how emission, reflection, and dark nebulae can overlap. The inner region glows in hydrogen emission. Around it rides a pale blue halo from dust that reflects starlight. Cutting across are the dense dust lanes that block light. The combination gives the Trifid a clean, symmetrical look that stands out even in small telescopes. Long exposure images bring out the lilac blend where red emission and blue reflection overlap. At the Trifid's center, a young, massive star supplies most of the UV that lights the gas. The same radiation pushes on dust farther out, shaping a layered structure, bright core, blue reflection ring, and dark cuts. Ionization fronts thin surfaces where UV-lit gas meets colder gas trace arcs across the face. Behind those fronts, pressure drops and gas can cool. In some spots, small globules form at the tips of ridges. A few contain embedded sources visible only in infrared. The Trifid is smaller than the lagoon, but because it packages several types of nebula in one field, it is useful for showing how the same physics looks in different arrangements. The two regions sit in a rich part of the Milky Way, so depth matters. Along any line of sight there are foreground stars, the nebula itself, and background stars in the spiral arm beyond. Dust changes the colors of those stars through extinction and reddening. Observers account for this by comparing star colors to standard patterns and by using infrared and radio maps of dust to estimate how much dimming occurs along the path. Without those corrections, distance and brightness estimates can be off. Over long spans of time, both the lagoon and the Trifid will change shape and tone. Massive stars within their clusters will end as supernovae, sending shockwaves that heat, compress, and rearrange the gas. Some regions will clear, others will collapse, and the clusters themselves will open as their stars drift apart. What appears solid now is only a temporary balance of pressure, gravity, and geometry. The same physical forces persist, shifting from one part of the region to another as energy moves outward through the clouds. From Earth, these nebulae are among the most approachable sights in the Milky Way. The lagoon glows clearly in binoculars under dark skies. The Trifid is dimmer, but reveals its divided face through a small telescope when the air is still. Narrowband filters tuned to hydrogen alpha or oxygen light heighten the contrast and bring out the delicate filaments and dark lanes. In wide-field photographs, both fit comfortably within the same frame: red emission, blue reflection, and dark absorption interwoven. Though separated by several thousand light-years, their overlap along our line of sight lets us compare two stages of the same cycle in a single view. Some nebulae, by contrast, arrange themselves into cleaner, more geometric forms. The Rosette Nebula, a near-perfect ring, and the California Nebula, a long, diffuse ribbon, seem like opposites shaped by the same rule. One gathers around a crowded cluster, the other follows the reach of a single bright star. Together, they show how radiation, geometry, and local conditions combine to set the architecture of a cloud. The Rosette Nebula, NGC 2237-2239, sits about 5,000 light-years away in Monoceros. It spans roughly 100 light-years and shines strongly in hydrogen alpha, the deep pink-red light common in star-forming regions. At its center is the young open cluster NGC 2244. Hot O and B-type stars in that cluster pour out ultraviolet UV light and drive fast stellar winds. UV light strips electrons from hydrogen atoms, ionization, and the gas glows when electrons recombine. The winds push on the gas and dust, clearing a low-density cavity and leaving a bright shell. What looks like a flat ring is actually a three-dimensional bubble. We see its thicker rim, where our line of sight passes through more glowing material. Along the inner walls of the rosette, thin, bright rims mark where radiation heats the surface and where photoevaporation gas, drifting away from a sunlit face, slowly removes material. Where the advancing shell meets denser clumps, small pillars and knots remain. Their tips often show compact teardrop shapes. Inside those protected tips, the gas is cooler and molecules can survive, while the outer skin faces the cluster and steadily evaporates. The result is a lace of arcs, ridges, and finger-like features that trace differences in density left over from the original parent cloud. When hot interior gas finds a weak spot, it can escape. Astronomers call the resulting outflow a champagne flow. Imagine warm, ionized gas at slight overpressure inside a cavity that opens into thinner surroundings. Once a channel forms, gas streams outward and expands. This vent relieves pressure, thins the shell, and carries energy into the surrounding molecular cloud. Over hundreds of thousands of years, repeated flows and steady wind action enlarge the cavity and move the shell outward. Feedback from the central cluster does more than carve a ring. It sets the pace of new star formation around the rim. Compressed edges cool and grow denser. In some places, compact globules form small, cold, dusty clumps that can collapse under gravity when shielded from UV light. Radio and infrared observations reveal such globules around the rosette, a few already hosting embedded protostars that are still gathering mass. The cluster in the middle, the ionized shell, and the colder reservoir beyond act together. Heating and pressure from the center shape the shell. The shell concentrates gas. The concentrated gas feeds the next generation. The rosette's symmetry is striking, but it is not perfect. Some sections of the shell are thicker. Others are cut by dark lanes where dust blocks light along our view. Those differences record the original structure of the cloud and the directions of the strongest winds. Magnetic fields add another layer. Dust grains tend to align with field lines, so starlight passing through the shell becomes slightly polarized in a preferred direction. The field can guide flows along the rim and slow collapse across it, helping set where filaments form and which ones last. The rosette emits across the spectrum. In visible light, hydrogen alpha dominates, with oxygen and nitrogen lines adding contrast. In infrared, warm dust in the shell glows softly and embedded sources stand out. In radio, carbon monoxide and other molecules trace the colder gas outside the ring. X-ray data show hot gas inside the cavity where winds collide and shock. Each band isolates a different part of the structure. Hot interior, ionized shell, dusty ridges, and the cold reservoir that will supply future stars. Far away in Perseus, the California Nebula, NGC 1499, shows a different geometry. It is elongated, about 100 light-years long, and much narrower than the rosette. One star dominates its energy budget. Xi Persei, Menkeb, a hot O-type star nearby in the same region. Xi Persei's UV light ionizes hydrogen along a stretched face of a cloud, lighting it in hydrogen alpha and creating a faint, continuous glow. Because the source sits off to one side, the brightness gradient is smooth, brightest on the illuminated edge, fading across the filament with distance. The California Nebula is diffuse, with soft edges instead of sharp walls. Dust in and around the cloud scatters starlight. Shorter wavelengths scatter more efficiently, so a faint blue reflection component rims parts of the red emission. Deep images show thin, dark streaks where denser filaments block background stars. Spectra reveal the usual lines of an H2 region: hydrogen, oxygen, nitrogen, but their relative strengths change with density and temperature. Closer to Xi Persei, the gas is more ionized and hotter. Farther away, it is cooler and less ionized, and dust makes a stronger mark. Chemistry in NGC 1499 is driven by UV photons from Xi Persei. Photodissociation, the breaking apart of molecules by light, occurs along the sunlit face. There, carbon, and oxygen-bearing molecules split and reform, and ions such as C+ help cool the gas by emitting in far infrared lines. Deeper inside, shielded from direct UV, molecules survive, and dust grains collect thin ice mantles. The result is a layered structure, a hot, ionized skin, a warm, partially dissociated zone called a photodissociation region, and a colder, molecular interior. The California's shape reflects that layering, drawn out along a long front rather than wrapped around a central cavity. Set beside each other, Rosette and California show how geometry controls appearance. A cluster in the center tends to clear a rounded cavity and leave a shell. A single bright star to the side lights a long face and builds a gradient. Both are examples of stellar feedback, the ways stars change their birth clouds through radiation and winds expressed through different layouts of gas and dust. For instruments, they are a pair worth comparing: ring versus ribbon, central versus off-axis source, shell versus face. Not all striking clouds are bright. Some are defined by what they hide. Dark nebulae are cold, dense regions where dust blocks visible light from stars behind them. They are not holes, they are structures. Two widely seen examples are the Coal Sack near the Southern Cross and the Snake Nebula, Barnard 72 in Ophiuchus. Both stand out because they sit in front of rich star fields, making their outlines easy to trace by contrast. The Coal Sack is a large molecular cloud roughly 600 light-years away. To the unaided eye, it looks like a broad patch of darkness cutting into the bright band of the Milky Way. Infrared and radio observations show a cold interior only a few degrees above absolute zero, and abundant molecules such as carbon monoxide and ammonia. In visible light, dust grains absorb and scatter more blue light than red, so background stars look dimmer and redder near the cloud's edge, and in the densest parts, they vanish from view. From a physics standpoint, the Coal Sack is a shielded environment where molecules survive and where gravity can act with fewer interruptions from external radiation. Inside the Coal Sack, small density variations grow slowly. Gravity gathers material into cores, compact regions a fraction of a light-year across, with enough mass to collapse. As a core contracts, it heats. When the center becomes dense and hot enough, a protostar forms. Later, as infall slows and a disk grows around the young star, the first light leaks out in infrared. Seen from a distance, the development looks like darkness, slowly pricked by faint, warm points, then brighter sources as the cocoons thin. The Snake Nebula is smaller, but sharply defined. It appears as a dark, shaped filament crossing a rich field of stars in Ophiuchus. The filament is only a few light-years long and less than a light-year wide, yet it stands out because the backdrop is so crowded with starlight. Magnetic fields and turbulence likely helped shape its curve. Along the length, observers find tiny dense cores and a few embedded protostars. Radio maps trace CO along the filament, while far infrared data show dust shining weakly. The compact warm points, sometimes seen near bends, are young sources beginning to heat their surroundings from within. Filaments such as the snake are common in molecular clouds. They act as channels that feed mass into growing cores. Gas flows along the filament under gravity. Where flows meet, or where the filament kinks, density rises and a core can form. Measurements of motion using the Doppler shift reveal small velocity changes along these structures, showing that material is indeed moving inward. Polarization studies add the direction of the magnetic field. which often runs along or across the filament and can help or hinder collapse depending on orientation. Dark clouds are also shaped by what happens outside them. Nearby bright stars can light the edges by reflection or weak ionization, producing thin, bright rims. Passing shockwaves from older supernovae can compress one side, creating a sharper boundary and sending ripples through the interior. Over long periods, some parts disperse, while other parts collapse. When a young cluster switches on inside a cloud, UV light and winds eat into the parent material from the inside, breaking the silhouette into pillars, globules, and arcs. The tools used to study these clouds match their conditions. Visible light images show silhouettes and dust lanes. Infrared maps reveal warm dust and the youngest objects still wrapped in their cocoons. Radio spectroscopy tracks molecules and measures temperature, density, and motion. Combined views build a practical picture, where gas is ionized or neutral, where dust is thick or thin, where shielding allows chemistry to proceed, and where gravity is taking hold. For observers under dark skies, the rosette appears as a round, low-contrast haze with a central star cluster, improved by a hydrogen alpha or O3 filter. The California Nebula is broad and faint. It favors very wide fields and long exposure imaging. The coal sack is visible to the eye from the southern hemisphere as a stark notch beside the Southern Cross. The snake requires a telescope and steady air. It shows as a thin, dark curve against a heavy star background. Knowing the layout behind those outlines turns each patch into structure, a real arrangement of gas and dust rather than a trick of the eye. Star formation begins inside cold, dark molecular clouds, large regions of gas and dust, where starlight is weak and temperatures are only 10-20 K, about 441 to 424 degrees Fahrenheit. A molecular cloud is mostly hydrogen, with helium and a trace of heavier elements and dust grains. The material is not uniform. Small differences in density, temperature, turbulence, or magnetic field strength make some spots slightly thicker than others. Gravity acts more strongly on those thicker spots, drawing in nearby gas. Over time, the cloud breaks into fragments a few light years apart. A light year is about 6 trillion miles, 9.5 trillion kilometers. Each fragment can become the seed of a future star cluster. Inside a fragment, collapse continues toward a dense core only a few thousandths of a light year across. Collisions among gas particles convert gravitational energy into heat. The core warms relative to its surroundings and becomes more opaque to its own radiation, which slows the rate at which heat can escape. Collapse proceeds, but not as a free fall. The core also begins to rotate. Angular momentum, the tendency for spinning motion to continue, means that as the collapsing region shrinks, it spins faster, like a skater drawing in their arms. Rotation prevents a purely spherical collapse. Gas flattens into an accretion disk, a thin, rotating structure that feeds material toward the center while keeping the system stable. Dust grains in the disk absorb starlight and re-emit it in the infrared. The center warms into a protostar, a hot object not yet powered by nuclear fusion. Material falling from the disk onto the protostar releases energy at impact, adding to the heat. The protostar is hidden in visible light by dust but radiates in the infrared and millimeter bands. Observations at those wavelengths reveal the disk, the envelope of infalling gas, and the temperature structure around them. Many protostars launch narrow, opposite flows called bipolar jets. They are fast streams along the protostar's rotation axis. Magnetic fields threading the disk and the young star help extract angular momentum and channel gas into the jets. Where a jet hits the surrounding cloud, it creates a glowing shock knot. Astronomers call some of these knots Herbig-Haro objects. They emit in specific lines of hydrogen, oxygen, and sulfur, and drift measurably over years to decades. Jets and wider, slower outflows help regulate growth by venting momentum and energy, keeping the disk from dumping material inward too quickly. Within the disk, dust grains collide and stick, forming larger aggregates. Ice coatings on grains act like glue at low temperatures. Pebbles grow into kilometer-scale planetesimals, and gravity then speeds up growth. The disk evolves while the protostar still accretes. At the same time, ultraviolet UV light from nearby massive stars can erode the outer disk surface, a process called photoevaporation. So environment matters for how long gas remains available for building planets. As the core of the protostar grows denser and hotter, pressure and temperature rise. When the central temperature reaches roughly 10 million K, hydrogen fusion begins. In Sun-like stars, this proceeds mainly through the proton-proton chain. In more massive stars, the CNO cycle dominates. Fusion releases energy that pushes outward. When this outward pressure balances gravity's inward pull, collapse halts and the object becomes a main sequence star. Accretion tapers off. The surrounding envelope clears by a mix of infall, outflows, and radiation pressure. In many systems, the remaining disk persists as a protoplanetary disk with gaps, rings, and spirals, shaped by young planets and by gas dynamics. Timescales vary with mass. Massive stars collect material quickly and reach fusion in a few 100,000 years. Low-mass stars take longer, often a few million years. The path is the same: fragmentation, core formation, disk growth, outflows and jets, ignition of fusion, and the onset of a stable phase where the star's luminosity is set by its mass and fusion rate. Spectroscopy turns these stages into measurements. Lines shifted by the Doppler effect reveal infall and rotation speeds. Molecular lines such as CO trace cold gas in the envelope and disk. Hydrogen lines trace jets and shocks. Polarization of starlight shows the direction of magnetic fields through dust grain alignment. Infrared excess above a star's photospheric light indicates warm dust in a disk. Millimeter interferometers map dust rings and measure disk masses directly. Together, these tools build a step-by-step picture of how a quiet cloud becomes a system with a star and a developing set of planets. Later, when a sun-like star exhausts hydrogen in its core, its structure changes. The core contracts and heats. The outer layers expand and cool. The star becomes a red giant, large, luminous, and cooler at the surface. A red giant's extended envelope is only loosely bound. Stellar winds carry material away at rates much higher than during the star's youth. After the star's outer layers drift off, the compact hot core remains. Its temperature can exceed 100,000 K. This core emits strong UV radiation that ionizes the departing gas. The ionized gas glows in specific lines. This is a planetary nebula, a misnomer from early telescope views where the round shells looked like small planets. The planetary nebula phase is brief in astronomical terms, usually a few tens of thousands of years. Gas expands outward at 1030 kilometers per second, 619 miles. The central object, now a white dwarf progenitor, is Earth-sized but extremely dense. Over time, as the gas moves farther away, it thins and fades. The white dwarf cools slowly, shining first in the ultraviolet and visible, then mainly in the infrared. The Ring Nebula, M57, in Lyra shows a nearly circular, bright rim with a fainter outer halo. The ring is a shell, seen almost face-on. Spectra show strong hydrogen emission in the red and oxygen in the green-blue, near 500.7 nanometers, doubly ionized oxygen, O3. Nitrogen adds lines in the red. Expansion velocities from line profiles are about a few tens of km/s, and the central star is a hot, compact object that ionizes the shell. The apparent symmetry comes from a combination of the shell's shape and our viewing angle. The Dumbbell Nebula, M27, in Vulpecula, has two bright lobes separated by a narrower waist. The pattern can result from a denser equatorial region or the influence of a companion star that shapes the outflow into bipolar lobes. Magnetic fields can also guide the flow. The same emission lines dominate O, 3, H, alpha, and N2, but their relative strengths change across the nebula with temperature and density. Imaging through narrowband filters isolates each component, revealing how shocks and radiation set the details. The Helix Nebula, NGC 7293, in Aquarius, is one of the nearest planetary nebulae, about 700 light-years away. It appears as a large annulus, with a complex interior and a faint outer halo. High-resolution images show thousands of small cometary knots, dense clumps, with bright heads and faint tails pointing away from the central star. These knots likely form where instabilities and shadowing protect small pockets of gas and dust as the ionization front moves through. The knots evolve as radiation erodes them. Some will disperse, others persist longer in denser regions. The central star of the helix is a hot white dwarf candidate whose UV flux keeps the inner shell ionized. Shapes in planetary nebulae vary widely. Some are nearly spherical, others are elliptical, bipolar, hourglass-like, or multipolar, with several lobes. Causes include density patterns in the red giant wind, rotation, magnetic fields, and binary companions. If a companion orbits close enough, mass transfer or a common envelope phase can focus the outflow along specific directions, producing jets and symmetric lobes. In many systems, multiple shells testify to episodes of mass loss at different times, visible as nested halos around the brighter inner structures. Planetary nebulae are useful for measuring chemical composition. Emission lines provide electron temperatures and densities, which allow abundance estimates of elements such as helium, carbon, nitrogen, oxygen, neon, and sulfur. These values record how stars enrich the interstellar medium. Low and intermediate mass stars dredge up material from their interiors during the giant phases, adding carbon and nitrogen to their winds. When the nebula shells mix back into the surrounding gas, those elements become part of future molecular clouds. Observation methods mirror those used for star-forming regions but target different conditions. Optical spectra measure bright, forbidden lines in thin gas transitions that are rare in dense laboratory settings but common at nebula densities. Infrared data trace dust and molecules in the cooler outskirts. Ultraviolet spectra probe the hottest central regions. Expansion rates from line splitting give kinematic ages when combined with angular size and distance. Imaging polarimetry can reveal dust-scattering patterns near the inner rim, hinting at geometry that is hard to see in total light. The planetary nebula stage ends as the shell expands and fades below detectability. The central white dwarf then cools over billions of years, radiating away its stored heat. Cooling tracks depend on mass and composition. Nearby white dwarfs show a range of temperatures that match the expected slow decline in luminosity. In the interim, the region the shell occupied returns to the general interstellar medium. Gas densities fall back to typical values for the local environment, and dust that survived the UV exposure continues drifting with the galactic flow. Examples at different distances help set scales. M57's angular size of about 1 arc-minute corresponds to a physical size of roughly a light-year at its distance. The helix spans about a half degree on the sky because it is close. Even so, the shell's thickness is only a fraction of its radius. Velocities remain modest compared to supernova remnants, which often exceed thousands of kilometers s, but they are high enough that shell positions change measurably over decades in precise images. The full path for a sun-like star runs from cold cloud to main sequence to red giant to planetary nebula and white dwarf. The path for massive stars diverges after fusion of heavier elements, ending as a core collapse supernova. But the early steps, fragmentation, disk, jets, share the same physics. In both cases, the material between stars cycles through phases of cold, warm, and hot gas, and through states of neutral, ionized, and molecular forms that can be traced by their distinct spectral lines and by their emission at different wavelengths. Planetary nebulae show wide variety in shape. Some are close to spheres, like simple shells. Others are stretched, tilted, or divided into two main lobes. Symmetry depends on several factors: whether the star has a close companion, how fast it spins, how its magnetic field is arranged, and how the earlier stellar wind left the system. Many objects show more than one shell, evidence for repeated ejections as the star's outer layers lifted off in pulses. In all cases, the power source is the same. A hot central core emits intense ultraviolet UV light that ionizes the gas and makes it glow while the shell expands. Colors in images are not decoration, they track physics. Astronomers use narrow-band filters to isolate specific emission lines, thin slices of wavelength where atoms radiate. Hydrogen alpha at 656.3 nanometers appears red. Doubly ionized oxygen, O near 500.7 nanometers, shows as blue-green. Singly ionized sulfur, S, at 671.6 and 673.1 nanometers, contributes deep red-orange. Combining these filters produces the familiar palettes in photos. The mix changes across a nebula with temperature, density, and ionization state, so color differences reveal structure. Hot, highly ionized interiors, cooler, denser rims, shadows behind dust clumps where UV light is weaker. Planetary nebulae matter for more than appearance. Low and intermediate mass stars, roughly 0.88 solar masses, dredge up elements from their interiors during late stages and lose them in winds. The ejected gas adds carbon, nitrogen, and S-process elements to the interstellar medium. Dust forms as well carbon-rich grains and silicates that later seed molecular clouds. Without this recycling, future stars and planets would lack many of the materials needed for complex chemistry. Not every shell expands evenly. In bipolar and butterfly nebulae, gas flows out along two opposite directions and forms lobes. Between the lobes sits a narrow waist denser material in the equatorial plane. The Butterfly Nebula, NGC 6302, shows this pattern on a large scale. Its wings extend for light years, and the central source is an extremely hot remnant with a surface temperature above 200,000 K. UV radiation from the core keeps inner gas highly ionized. Oxygen and nitrogen lines dominate close in, while hydrogen and sulfur become stronger farther out as conditions cool. Dark bands across the waist mark where dust absorbs visible light and re-emits at infrared wavelengths. The term bipolar describes geometry, not cause. Several mechanisms can focus an outflow. A fast wind from the hot core can collide with a slower, earlier wind from the red giant phase. If that earlier wind was denser around the equator, it resists motion in the plane but allows easier escape along the poles. Rotation and magnetic fields can help maintain that waist. A strong magnetic field can guide charged gas along preferred directions, narrowing the lobes. In many cases, a close companion star shapes the flow. During a common envelope episode, the companion spirals into the giant's extended atmosphere, transfers angular momentum, and helps eject material in specific directions. The result can be a pair of well-matched lobes that stretch for light years while the waist remains compact. The Twin Jet Nebula, O-9, shows two narrow opposed lobes that look almost mirror-symmetric. At its center is a binary system. Gas leaves the dying star, interacts with the companion, and is funneled into a spiral before escaping along the poles. Knots at the lobe tips are shock fronts where the outflow meets slower material. Small differences in the two sides, one lobe slightly longer, one brighter near the base, hint at changes in the wind or orbital motion during ejection. Spectra taken along the lobes reveal velocities of hundreds of kilometers per second, and line ratios show where shocks and photoionization dominate. Many bipolar nebulae show signs of episodic events, nested lobes, overlapping shells, or faint outer halos tilted at angles to the main structure. These records allow astronomers to reconstruct timelines. A faster wind overtakes an older, slower wind and creates a bright rim. A later outflow at a slightly different angle cuts a new path. In images, shock boundaries appear as thin filaments. In infrared maps, warm dust outlines the waist. In radio, molecules trace cooler material, protected from UV light. Polarized light maps show the orientation of dust, grains, and give clues to magnetic field directions. Line emission provides measurements rather than impressions. Ratios like O3H beta or 9:2 alpha mark temperature and ionization. The S2 doublet ratio yields electron density. Broadening and splitting of lines give expansion speeds. Combined with angular size and distance, speeds lead to kinematic ages, often a few thousand to a few tens of thousands of years for bright structures, with older, faint halos extending beyond. These shells fade as the gas expands and as the white dwarf cools. Typical expansion rates for bright rims are 10-30 kilometers per second. Highly collimated flows can reach much higher speeds. Over time, edges blur, and the lobes merge with the surrounding interstellar medium. The leftover core continues to cool along a predictable track. In the meantime, the region around the object contains enriched gas and dust that later join new clouds. A different end is reserved for massive stars, a core collapse supernova. The Crab Nebula, M1, is the best-studied example of a young supernova remnant linked to a historical event recorded in 1054 CE. In telescopes, the crab appears as a filamentary oval about 10 light-years across. The filaments are cool, dense strands of ejected gas, rich in hydrogen, helium, oxygen, nitrogen, and sulfur. Between them lies a diffuse glow from high-energy particles. The entire structure is still expanding. Motions measured directly in images, taken decades apart, confirm speeds near 1,500 kilometers per second for many features. At the crab's center sits a neutron star, a compact remnant about 20 kilometers across, formed when the original star's core collapsed. The object is a pulsar that spins about 30 times per second. It emits beams across radio, optical, X-ray, and gamma-ray bands. As the beams sweep past Earth, they produce regular pulses. The pulsar drives a wind of relativistic particles, electrons and positrons that fill the inner nebula. As these charged particles spiral in magnetic fields, they produce synchrotron radiation. Synchrotron emission makes a smooth, continuum glow from radio to X-rays and outlines a torus and jet structure near the pulsar in high-resolution images. The bright filaments trace where supernova ejecta have cooled and recombined. Emission lines identify their makeup. Oxygen contributes strong green-blue lines. Hydrogen and nitrogen add red, and sulfur provides deeper red features. Filament positions change over time. Some stretch and thin, others brighten where a pressure wave crosses. Velocities vary along each strand, showing that the ejecta are not a single shell but a layered, tangled structure shaped by both the original explosion and later pressure from the pulsar wind. Time variability is one of the crab's key features. Close to the pulsar, X-ray images show wisps that move outward over months, marking waves in the wind zone. Optical pictures reveal knots that shift year to year. Radio maps track the larger, smoother component of the synchrotron cloud. Because the crab is bright across the spectrum, it serves as a test ground for particle acceleration and magnetized plasma. Field strengths near the pulsar are enormous compared with everyday values, and the flow speeds are a significant fraction of light speed. Models tuned to match the crab's torus, jet, and moving wisps are checked against both images and spectra. The crab's total energy output combines several parts: kinetic energy of the ejecta, energy stored in magnetic fields, and the power of the pulsar wind. Most of the visible light brightness comes from synchrotron radiation plus line emission from the filaments. In X-rays, synchrotron dominates. In radio, it also dominates, but traces lower energy electrons spread more widely. The filaments show up strongly in optical lines and in infrared where warm dust emits. The dust likely formed from ejecta or from material swept up and processed by the shocks. Spectral signatures of silicates and carbonaceous grains appear in the mid-infrared, and their temperatures indicate gentle heating by the surrounding radiation. Kinematics connect the present nebula to the 1054 event. Extrapolating filament motions backward gives an origin date close to the historical records. The expansion is not strictly uniform pressure. From the inner wind modifies speeds, so more detailed fits account for acceleration and deceleration in different zones. The neutron star's spin is slowing over time as it loses energy to radiation and the particle wind. The rate of slowdown matches the power needed to maintain the inner nebula's brightness and motion, linking the compact engine to the broader glow. Distance and scale set context. At roughly 6,500 light-years away, The crab spans about 5-6 arc minutes on the sky. A single filament can be a fraction of a light-year thick, yet carry enough mass to stand out clearly in emission lines. Shock speeds vary. Slow shocks excite strong optical lines. Faster shocks add ultraviolet and X-ray components. Where shocks cross denser clumps, they compress and heat the gas, then cool and leave thin, bright edges. Where the medium is thinner, shocks broaden and the emission spreads. Different bands reveal different structures. Radio observations map the extent of low-energy synchrotron emission and show the large, smooth halo. Optical images isolate line-emitting filaments and allow velocity measurements through Doppler shifts. Near-infrared maps record warm dust in and around the filaments. Mid-infrared spectra measure grain composition. X-ray images highlight the inner torus, jet, and moving wisps tied to the pulsar wind. Gamma-ray detections record the highest energy particles and flares from the pulsar. Together, these diagnostics tie element abundances to flow speeds and link the pulsar's energy output to the shapes and motions seen across the remnant. The Crab Nebula shows motion on several tempos at once. The central pulsar spins about 30 times per second. Close in, wisps move outward over months in X-ray and optical images. Farther out, filaments creep over years and decades. Cooling in the gas continues over centuries. Each layer has its own pace because the energy sources differ. The pulsar wind drives the inner glow, while the outer net of filaments records the original ejector and the shocks running through them. The nebula looks delicate in long exposures, yet it holds kinetic energy from a supernova and steady power from a neutron star that is still slowing as it radiates. Light travel time puts the view in context. The photons arriving tonight left the crab about 6,500, 7,000 years ago, long before observers in 1054 wrote about the daylight guest star. By the time the historical flash reached Earth, the expanding debris was already far from the core. The pulsar will eventually spin more slowly, and the synchrotron glow will fade, but the elements driven into space, carbon, oxygen, silicon, iron will continue to mix into nearby clouds where future stars can form. The object is a young supernova remnant powered by a compact engine, not a final state. A supernova is brief. The remnant lasts far longer. As the shock front travels outward, it encounters an uneven interstellar medium. In low-density regions, it moves quickly and dims. In denser regions, it slows, compresses gas, and brightens. Thin sheets become visible where we see the shock nearly edge on. The Veil Nebula, in Cygnus, is a clear example. It lies roughly 2,400 light-years away and spans more than 100 light-years. What looks like a tangle is a set of rippled shock fronts: the Eastern Veil, the Western Veil, the Witch's Broom, and Pickering's Triangle. Hydrogen emission appears red, oxygen blue-green, sulfur deep red-orange. The colors map temperature, ionization, and density. Viewed face-on, emission looks like a soft glow. Along the edge, it sharpens into threads thinner than a light-year. The veil's expansion is measurable. Comparing images separated by a few decades shows outward motion. Line profiles reveal speeds of a few hundred kilometers per second, depending on location. Where the shock first hits neutral gas, a non-equilibrium zone forms. Atoms are excited and ionized at different rates, giving a characteristic set of lines. Farther behind the front, gas cools and recombines. Magnetic fields influence the shape of fine filaments by guiding charged particles and stabilizing some layers against small-scale breakup. Radio maps show diffuse synchrotron emission from accelerated electrons, tracing places where the shock efficiently speeds up particles. The Vela supernova remnant in the southern sky is closer, at about 800 light-years, and older, around 11,000 years. It covers a region over 8 lunar diameters wide. Because it is close, small features resolve clearly. Arcs, knots, and overlapping loops formed, where shocks collided with denser clumps. The Vela pulsar at the center spins about 11 times per second and powers a compact inner nebula. Its energy is modest compared with the Crabs, so the larger structure is dominated by the cooling and mixing of ejecta with the local medium. Radio, optical, and X-ray maps together outline multiple shells and filaments at different temperatures. Regions where the remnant overlaps older structures, like the Gum Nebula, show layered arcs along the same line of sight. Remnants like the Veil and Vela are practical laboratories. They show how shocks compress and heat gas, how turbulence grows behind a front, and how heavy elements disperse. Observers use line ratios to estimate electron temperature and density, and use Doppler shifts to measure motion along the line of sight. Proper motions across the sky give transverse speeds. Combined with distances, these data produce expansion ages for different parts of a remnant. The agreement or mismatch with a single age indicates how much the environment has altered the flow. In each case, the thinness of bright filaments reveals a balance between heating and cooling. Where density is higher, cooling is faster and sheets are narrower. Where density is lower, the emitting zone is broader and fainter. Magnetic pressure can keep layers from collapsing and can also align strands. The result is a woven appearance that records local conditions rather than a single uniform shell. The fine structure is not decoration. It marks where energy is being deposited and how it is moving out of the system. South of our galaxy's midplane, a different kind of high-activity region sits in another galaxy, the Tarantula Nebula, also known as 30 Doradus, in the Large Magellanic Cloud, about 160,000 light-years away. It is a giant Cloud 2 region, where massive stars form in large numbers. The central cluster R136 contains several of the most massive and luminous known stars, many exceeding 100 solar masses. Their ultraviolet radiation ionizes hydrogen and other elements over hundreds of light-years. Their wind's fast flows of charged particles sweep bubbles into the surrounding gas. Where bubbles collide, dense walls form and can trigger new star formation by compressing gas. Because the tarantula sits above much of the dust in the Milky Way, instruments have a relatively clear view across wavelengths. Optical images show strong alpha and O3 emission that trace ionized gas. Infrared maps reveal warm dust in ridges and the glow from embedded young stars still inside cocoons. X-ray observations detect hot gas filling the interiors of large cavities where winds and past supernovae have heated material to millions of degrees. Radio data trace cold molecular gas, the fuel for future stars, around the edges of ionized zones. Together, these data show a network of cavities and shells, with star formation concentrated along compressed boundaries. R136 sets conditions that push local physics to extremes. Radiation pressure and winds from many O-type and Wolf-Rayet stars act together, not in isolation. Gas pressures are higher than in nearby smaller regions like Orion. The number of very massive stars increases the rate of feedback events. Supernovae from earlier generations within 30 Doradus have already added energy and heavy elements. Those elements alter cooling rates because metals radiate energy efficiently through many lines. The mix of radiation, winds, and heavy element cooling shapes how quickly gas fragments and how long dense ridges survive before eroding. The tarantula's size allows multiple scales to be studied at once. On the smallest accessible scales, narrow filaments and pillars mark where shielding allows molecules to persist. On intermediate scales, arcs trace expanding shells tens of light years wide. On the largest scales, linked cavities hundreds of light years across show where clusters have evacuated volumes of gas. Kinematic maps made by scanning spectrographs reveal expanding rings and bubbles centered on young clusters, and also show where flows intersect. In those intersections, shock heating and turbulence raise temperatures and seed new instabilities. Within the ridges, protoplanetary disks and compact clusters form. Infrared excesses around many young stars indicate warm dust in disks. Submillimeter arrays map rings and gaps in some disks, evidence that dynamical processes and possibly young planets are already shaping the material. Close to the brightest sources, photoevaporation can remove disk gas quickly. In more shielded pockets, disks last longer. The distribution of disk lifetimes across the tarantula constrains how environment controls planet formation around young stars of different masses. The tarantula also links local star formation to galaxy-scale behavior. Starburst regions, areas where galaxies form stars at high rates, show strong feedback that can both start and stop collapse. In 30 Doradus, feedback collects gas into dense walls, where it can collapse again, but also clears large cavities, where star formation pauses. The balance depends on gas surface density, radiation field strength, and how quickly cooling allows compressed gas to fragment. Because the Large Magellanic Cloud has lower average metallicity than the Milky Way, cooling and dust shielding differ slightly from nearby regions, providing a comparison set for how chemistry changes the outcome. Observationally, 30 Doradus is used to calibrate methods that are then applied to distant galaxies. Integrated light from the tarantula can be measured as if it were far away. Line ratios from H-alpha, O3, Num2, and S2 define diagnostics for temperature, ionization parameter, and metallicity. Comparing those integrated values to resolved maps checks how well global measures represent the real mix of conditions inside a complex region. Similar tests use infrared fine structure lines and radio recombination lines to trace density and temperature where dust is heavy. Feedback leaves imprints that are easy to find with time series. Expanding shells develop rims that brighten and split as faster winds catch slower gas. Broadening in line profiles shows multiple components along a single line of sight. Proper motions over a few years are small at the tarantula's distance, but radial velocities from spectra still separate expanding features from static backgrounds. Combined with stellar ages in clusters, these motions help reconstruct the sequence of events: which clusters formed first, which shells they drove, and where later star formation began along those shells. The Large Magellanic Cloud's position gives another advantage: low foreground extinction and high angular size for its distance. The tarantula spans more than 1,000 light-years, yet details down to a fraction of a light-year can be resolved with modern instruments. That combination of scale and clarity allows tests of models that couple radiation, hydrodynamics, magnetic fields, and gravity. Simulations that reproduce the observed cavity sizes, shell thicknesses, and line ratios gain credibility when applied to more distant systems where only integrated light is available. Massive stars in R136 will end as core collapse supernovae. Before that, many already shed mass via winds, enriching the local medium. When supernovae occur, they will drive fresh shocks through the same ridges that formed under earlier feedback. Those shocks will compress some zones and clear others. Young clusters now embedded will emerge into low-density cavities. Older shells will merge with newer ones, building larger structures. Dust will be destroyed in hot shocks and reformed later in cooler gas, altering infrared emission patterns. Each step is observable at different wavelengths with current facilities. In the northern and southern sky alike, the tools do the same work. Narrowband imaging isolates specific ions to map temperature and ionization. Broadband infrared maps dust temperatures and distribution. Radiospectroscopy traces cold molecular gas and measures velocities. X-ray imaging shows hot plasma in cavities. Polarization measurements reveal magnetic field geometry through dust alignment. Time baselines, even of a few years for nearby remnants, and of a few decades for the closest pulsar wind nebulae, add motion to the maps. The combination turns striking images into measurements that follow how energy flows from compact sources and young clusters into the gas around them. Between the bright ridges and dark lanes, space looks quiet. It isn't. The same processes that shape giant regions like the tarantula also work here in the Milky Way. The pattern repeats. Clouds form, stars switch on, radiation and winds push back, and the material cycles again. A nebula is not a static picture. It is a moving network where gravity, light, and chemistry build structure step by step. Deep inside cold molecular clouds, chemistry takes the lead. These clouds are mostly hydrogen gas with helium mixed in and a small amount of dust. Temperatures hover only a few tens of degrees above absolute zero. At those temperatures, hydrogen molecules, H2, are hard to detect directly because they emit very weakly. Carbon monoxide, CO, becomes the marker instead. CO has rotational transitions that glow at millimeter wavelengths, so radio observatories can map CO and through it infer where most of the hydrogen mass sits. When astronomers trace CO, they are tracing the outlines of the cold reservoirs where stars will begin. The maps show broad clouds stretched along spiral arms with dense knots and long filaments. Inside the densest parts, atoms and molecules collide just often enough to stick. Oxygen and hydrogen form water. Carbon and oxygen form CO and CO2. The dust grains, tiny solids of silicate or carbon, act like workbenches. They collect thin ice mantles made of water, carbon dioxide, ammonia, and methanol. On these icy surfaces, slow photochemistry runs. A cosmic ray, or a stray ultraviolet UV photon, breaks a bond. Fragments recombine into new molecules. Over long times, the ices grow more complex. Simple organics appear: alcohols, aldehydes, and longer carbon chains that store energy in their bonds. These same kinds of compounds show up in meteorites that fall on Earth. Their spectra match the signatures measured in space: features of water ice, CO2 ice, and organic residues. The link shows that the chemistry in cold clouds feeds directly into young planetary systems. When a protostar warms its surroundings, the ices evaporate. Molecules return to the gas where they can be detected again and then refreeze later as the environment cools. The cycle can repeat many times as gas flows through a region. Some molecules make very clear signposts. Polycyclic aromatic hydrocarbons, PAHs for short, are flat ring-shaped molecules made of carbon and hydrogen. When UV light hits a PAH, it vibrates and releases energy in specific mid-infrared bands. Those bands line spiral arms in mid-infrared surveys like a set of neon outlines. Because PAHs respond to UV light, they tend to glow near young stars, so their emission traces places where massive stars have recently formed. Similar ring structures form the backbone of many useful molecules in living systems. But in space, PAHs are simply stable carriers of energy and markers for where dust and gas sit under UV exposure. Visible light can't reach into cold clouds easily. Dust scatters and absorbs it. Infrared and radio light pass through with less trouble. That is why instruments working at longer wavelengths became the main tools for interstellar chemistry. The Spitzer Space Telescope mapped the mid-infrared glow from PAHs and warm dust, outlining the galaxy's structure from another angle. ALMA, the Atacama Large Millimeter, Submillimeter Array, resolves disks around young stars and detects faint lines from methanol, formaldehyde, and other organics. The James Webb Space Telescope now adds sharp views of ices and molecules in both emission and absorption. In those data, every bump in a spectrum marks a bond, stretching or bending. By reading the pattern, astronomers identify the species present and estimate their amounts. Chemistry in these regions is slow but persistent. Dust grains catalyze reactions that would be unlikely in thin gas. Cosmic rays keep a low-level ionization background alive, which helps some reactions start. Over millions of years, small molecules build into bigger ones. When collapse begins, the chemical inventory flows inward. Some material falls onto the forming star. Some stays in the disk. Heating near the star drives a snowline pattern in the disk. Inside certain distances, ices evaporate. Farther out, they stay frozen. This simple temperature rule shapes where different molecules are available to build planets and where solids can grow quickly. Where new stars switch on, their energy changes the scene. The star's light ionizes nearby hydrogen, making a warm, faintly glowing bubble. Winds from young massive stars carve cavities and pile gas into ridges. In those ridges, density rises. Gravity begins to win again in small pockets. The process is patchy rather than smooth. Triggered star formation can appear along the edges of a cavity where compression is strongest. In radio maps, carbon monoxide outlines these arcs. In infrared, warm dust draws their bright rims. In optical narrowband images, hydrogen alpha, oxygen, and sulfur lines trace the ionized layers. The connection between chemistry and structure is direct. Where dust is thick, shielding is strong, and molecules survive. Where UV light is strong, ices evaporate and PAHs glow. Instrument teams use all of these clues together to build a picture. CO for mass, PAHs for UV exposure, thermal dust emission for temperature, and line ratios for density and ionization. With these layers aligned, a three-dimensional view emerges of how gas flows, collapses, heats, and cools. The path from cloud to stars rarely runs to 100% completion. Only a small fraction of a cloud's mass becomes stars. This fraction, called the star formation efficiency, often sits around 10% for a whole region. The rest is heated, pushed, and stirred until it drifts away. Massive stars set the pace. Their radiation and winds provide the bulk of the momentum that clears cavities. After a few million years, the first supernovae add stronger shocks that speed the clearing. By then, most of the gas that will feed the first generation in a cluster has already been used or removed. As gas peels away, the newborn stars become visible. What had been a fog with hidden lights becomes a loose group shining without a veil. The group's fate depends on how much mass it holds and how tightly bound it is. Compact, high-mass clusters can remain gravitationally bound for long times. Loose associations often disperse within a few 100 million years. The members spread along the galaxy's orbit, forming long streams that can be traced by shared motion and chemistry even after the original cluster dissolves. The mix of star masses in a newborn group follows a pattern called the initial mass function. It is a statistical rule. A few massive stars, more sun-like stars, and many low-mass red dwarfs. This pattern appears in many places and epochs. It sets the long-term budget for light and heavy elements. The most massive stars live short lives and make large changes. They return oxygen, silicon, calcium, and iron to the gas. Low-mass stars burn slowly and remain as steady sources of light for billions to trillions of years. Together, they shape a galaxy's brightness now and its chemistry later. A cluster's early years are crowded. Gravity binds, the stars close. The group orbits the galaxy through spiral structure, dark clouds, and stellar neighborhoods. Tidal forces from the galaxy and encounters with other objects rearrange orbits. Over time, the group stretches, stars peel off. The Pleiades and Hyades are nearby examples of open clusters that formed from similar processes in the Milky Way. Many bright stars in Earth's night sky likely started life in clusters that have since faded from view as distinct groups. Their family ties are detectable in their shared chemical fingerprints and similar motions even if they no longer sit together. The gas that leaves a nebula is not waste. It returns to the interstellar medium, the galaxy's broad reservoir of diffuse gas and dust. There it mixes with material from many other sources. Slower winds from red giants, faster winds from hot stars, shells from planetary nebulae, and ejecta from supernovae. The mixture carries the products of stellar fusion. Over time, the average heavy element content, the metallicity, rises. Cooling becomes more efficient because atoms with many lines can radiate energy away quickly. Dust formation becomes more common. These changes feed back into how future clouds cool and how easily they collapse. The cycle runs on several clock speeds. On the scale of a region like Orion, the march from dense clump to a young cluster can take a few million years. On the scale of spiral arms, gas collects, forms stars, and is pushed out over tens of millions of years. On the scale of a galaxy, star formation ramps up and quiets down in broad waves that last hundreds of millions of years. The same rules apply at each scale. Gravity pulls material together, pressure, heating, and magnetic fields resist. Radiation and winds provide feedback that rearranges the outcomes. Measurements turn these ideas into numbers. Star formation efficiency is estimated by comparing the mass in young stars to the mass of the nearby gas. Outflow rates are measured from the brightness and velocity of specific lines. Dust content is measured from infrared emission curves. Metallicity is measured from line ratios calibrated in H2 regions and young stars. In nearby clouds, proper motions and radial velocities connect member stars to their birthplaces. In more distant regions, integrated light provides averages over many parts. The role of PAHs and other small grains is more than cosmetic. They absorb UV photons and re-emit in the infrared, helping regulate gas temperature in exposed layers. They provide surfaces for molecules to form and places for charge to collect. Their abundance changes in harsh radiation fields. Near very hot stars, PAHs can be destroyed, and their mid-infrared bands weaken. By mapping those bands, observers infer where radiation is strong and where shielding is effective. ALMA maps disks around young stars at high resolution. Rings and gaps appear in many disks. Some gaps may be carved by forming planets. Others may be caused by snowlines or pressure bumps in the gas. Chemical maps show where CO remains in the gas and where it is frozen out. JWST adds spectra of ices in absorption against background stars or bright nebula areas, isolating features from water, CO, 2CO, and organics. Together, these observations place the chemistry of clouds into the context of planet formation, showing which molecules are present where solids are growing. As clusters emerge from their clouds, radiation pressure and winds continue to act. Gas blowout is not a single blast, but a long push. Surfaces wrinkle where flows meet. In some directions, the shell finds an easy path and opens a channel. In others, it stalls against denser pockets. Ionization fronts trace the edges of these changes in narrowband images. In radio, the atomic hydrogen outside the ionized zone shows how far the feedback has run. In X-rays, hot gas marks the hidden interiors of the cavities cleared by winds. Once free of their birth fog, clusters move as units until tides and encounters scatter them. The stars that break away drift into the field population. Chemical tagging, the comparison of detailed element patterns, lets astronomers search for long-lost siblings spread across the sky. Stars born together often have nearly identical patterns of dozens of elements, a signature acquired from the same parent cloud. Combined with precise motion data, those chemical links help reconstruct where a star started, even when the cluster itself has vanished from sight. The stars remember, even if the nebula does not, and the circle closes again. Gas gathers, a star lights, winds carve the cloud, the shell drifts and thins. What fades returns to the dark, and the dark holds the next beginning. A glowing nebula is not decoration, it is work in progress. In these clouds, light meets matter, and simple rules, gravity, heat, motion turn into color and shape. Hydrogen blushes red, oxygen glows blue-green. Sulfur runs along the edges like a quiet line of orange. Pillars stand where dense gas resists. Rings appear when a star lets go. Fine threads stretch where shocks pull the fabric thin. Up close, the scene is orderly. Energy in, energy out. Atoms changing partners at a careful pace. Across many regions, the pattern repeats. Gas collapses into stars. Stars light and sculpt the cloud. Their ends return metals, dust, and heat to space, priming the next collapse. It is not waste, it is renewal. The galaxy keeps its own house, sweeping, sorting, and starting over so the long rhythm holds steady even as any single glow fades. Let the last images ease to dim. Picture a quiet lane of dust, a slow ripple of red light, a cluster breathing free as the fog that hid it drifts away. The night is patient. The chemistry is patient. Somewhere, far from any city and beyond any map, another cold knot is gathering itself toward a spark. The sky will carry that light in time. For now, let it be enough to know the work continues soft, steady, and sure out there between the stars.